Dr. Munji in today's video is going to cover a review of Hooke's law and Poisson's ratio. Today we're going to go over the stress-strain diagram, just in a little bit of detail, not full detail. Then we're going to move into Hooke's law, Poisson's ratio, go over an example problem, and then I'm going to leave you with a practice problem to try what we learned today on your own. So we have another video for you that actually goes through in a little more detail this stress-strain diagram, okay? But I wanted to give you this image from the book, from Hibbler's book here, that shows you an overview. So what we have here, we have four parts of the stress-strain diagram. The first part we call the linear elastic region of the diagram because it is a linear function, as you can see, a straight line. I'm going to highlight this. From here to here. Maybe I'll use a different highlighter color so we can actually see. There we go. Okay, that's the first portion. After we have loaded the system and we are kind of getting past the elastic region, we have a portion of the stress-strain diagram that is called yielding, from here to here. After yielding, we have strain hardening, where we see an increase in stress and strain, but in this curved form, no longer linear and no longer just straight across where we're increasing the strain but not increasing the stress. And then we get to a point where the system cannot take any more load. It is stressed to the max. We reach the ultimate stress and it starts declining until it fractures. That is called necking. Okay. I'm not going to go into detail about every single one of these parts in this video, but right now what I want to focus on is this first part, which is the elastic region. And I want to talk about a couple of formulas that we're able to apply to the elastic region. One of those formulas is called Hooke's law. You may have learned about Hooke's law in a few classes now, mainly physics, right? So we use Hooke's law in different ways. We use it for spring forces. We also use it to relate stress and strain to each other, okay? So I'm going to write down Hooke's law. Sigma is equal to modulus of elasticity times epsilon, okay? Now, what is sigma? What is E? What is epsilon? Sigma represents the normal stress. E represents the modulus of elasticity. This is also called Young's modulus. So if you're looking at a resource and it says Young's modulus, this is the same thing as a modulus of elasticity. This is dependent on the type of material that we have. So the modulus of elasticity is going to be different for a material like steel versus a material like concrete. Epsilon is the strain. And in this case, it's the normal strain because we're writing this formula in terms of normal stress and strain. Okay. What this tells us, this formula, Hooke's law, we're able to use this formula, I'm going to pull back here, anywhere in that linear elastic region, but nowhere else. Why? Because it's a linear formula, right? Sigma equals E times epsilon. You see how this is just a linear function, right? I'm going to show you from kind of math, right? So we have y equals mx. Why don't we have the b? Well, we do, but b is 0. It goes through the origin. So plus 0. This is just the function of a straight line. So that means that if we're comparing this to a function of a straight line, my e value is the slope of the line. So we can actually calculate the modulus of elasticity roughly if we're given the stress-strain diagram for a material. Okay, and the sigma is my y value. Makes sense because it's on the y-axis. And the epsilon is my x value. Makes sense because it's on the x-axis. So as long as we're in the elastic region where we have elastic behavior, we are able to use Hooke's law for stress, strain, and modulus of elasticity. This increase in stress during that region causes a proportional increase in strain. So this proportional or linear variation is why we're able to use Hooke's law in that portion of the diagram. Okay. The other refresher I want to go over today is Poisson's ratio. So Poisson's ratio gives us basically a ratio between the lateral strain and the longitudinal strain of an element. So I want you to think of something that you have in your hands, like that's kind of rubbery, okay? And let's say you're pulling on that system. As you pull on that system, you're increasing in the longitudinal direction, you're becoming longer, but you're decreasing in the lateral direction, it's becoming smaller, right? So you can use this as an example. I'm increasing the length as I pull on this system, but you can see the width is decreasing, right? This is more width, less length, more length, less width. That's what's happening. And we can actually use Poisson's ratio to tell us the ratio between how much we're decreasing in the lateral direction, how much we are increasing in the longitudinal direction. And I've written that here for you. Why is there a negative sign? Because as one dimension gets longer, the other dimension gets shorter. So that is inverse, right? Because it is an inversely proportional relationship, we need to put the negative sign there. For Poisson's ratio, we usually use the Greek letter nu, this kind of fancy looking V, and that is equal to negative epsilon lat, which is the lateral strain, divided by epsilon longitudinal long, which is the longitudinal strain. Okay, now that we know, or we've got a little bit of refresher on what Hooke's law is and what Poisson's ratio is, let's go ahead and solve for this example. So we have a bar of A36 steel, and it has the dimensions shown in this figure below. We have an axial force pulling on the bar, just like my hands were pulling on that tie. We have an axial force of P equals 80 kilonewtons pulling on the system. And we want to determine the change in length and the change in dimensions of the cross-section after we apply the load. And we're being told, which is very important, I'm going to highlight this, the material behaves elastically. What does that mean? It should ring a little bell. We can use Hooke's law. Okay, let's go ahead and set this problem up now. So we have here, basically, we're going to start with calculating the normal stress in the bar. Sigma, normal stress in the bar, is equal to force divided by area. And we're given those, right? We're given that. So what's the force? 80 kilonewtons. I'm going to put this into newtons. What's the cross-sectional area of the bar? 0.1 meters times 0.05 meters. And I get 16 times 10 to the 6 pascals. Now, this would be given to you, or you could figure this out from the table in the code book, but A36 steel, which it is given in the problem here, has an E value of 200 gigapascals, okay? You can get this value again from the code, or this would be provided in the problem to you, okay? Eventually, whenever you see A36 steel, you'll kind of remember the value of E for those types of members, because those are very common types of materials that we use. But for now, it'll be given. Okay. Now we can calculate the epsilon, the normal strain, by taking the sigma divided by E. Where did I get this formula from? Well, remember, it's Hooke's law. I just rewrote it. Sigma equals E epsilon. Well, I can rewrite this to say epsilon is equal to sigma over E, right? Okay, let me plug in what I have. 16 times 10 to the 6 pascals divided by, what's the E value? 200 gigapascals. So I'm going to say 200 times 10 to the 9 pascals. And that gives me 80 times 10 to the negative 6 millimeters per millimeter. Remember, strain is a dimensionless unit. We usually define it as length divided by length. Okay. Now what can we do? We have the stress and we have the strain, but we want to know what the elongation of the member is. So axial elongation. What is that? Well, let's apply that formula, right? So let's apply the formula first for what we know about strain, okay? We have delta, the change, is equal to epsilon times the length, right? Where did I get this formula from? Or you can either write delta like this, or you can write it like this, delta L. Well, epsilon is equal to delta L over L. Same thing as saying delta over L. You can use either notation that you like. Okay, they're both the same thing, delta L or the lowercase Greek letter delta. Okay, so delta is equal to epsilon L. That is the same equation as this right here, which is the definition of strain. And what we can do is we can say, well, we have the strain. This is in the z direction, right? This is all in the z direction. We have the strain in the z direction. We calculated that. That is going to be the 80 10 to the negative 6 millimeter per millimeter. And we have the original length of the member, right? What is the original length? 1.5 meters, right? Given in the problem. If I multiply both of those out, I get 120 micrometers. That is my delta L. But that is in the axial direction. I want to know what it is now in the lateral direction. So this is part of my answer. What do I do to get it in the lateral direction? So the contraction. I can use Poisson's ratio to relate the longitudinal direction to the lateral direction. So I can say that my EX, which is equal to my EY, because this is a symmetric element in those directions, equal to negative nu epsilon in the Z direction. Where do I get Poisson's ratio? I get it for A36 steel. Even if you were to Google this, you'd find it. This is equal to 0.32. If I plug all of this in, I end up getting that lateral contraction is negative 25.6 micrometers per meter. Okay, now highlight this. Why is it negative? Because remember, as we increase in the axial direction, we get smaller in the lateral direction. Okay, so that is the end of this example problem. I'm going to leave you here with a practice problem so that you can try to apply what you've learned today on your own.